Good morning. Thank you for joining today's webinar, Cell Can to Battery Module, Boost HEV Battery Performance Through Simulation. Just a couple of quick slides I'd like to go through with you before I hand things over to our presenter today. Okay, well, you have two speakers today. The first speaker as a video component is Dr. Robert Spotnitz. Bob leads Battery Design LLC, a company that develops software for battery design and simulation. He is a well-known speaker on various aspects of battery engineering. In 2009, Bob partnered with CD Adapco to support Battery Design Studio, a virtual environment for battery design and simulation. He received a PhD in chemical engineering from the University of Wisconsin-Madison. Following up from Bob, we have Gaetan Donblanc. Gaetan is a battery application specialist here at CD Adapco, working out of our London office. He has specialized in thermal management for battery design technology. He currently works on validation studies and applications within our products, both for battery simulation module and battery design studio. Okay, so with that, it's over to our first speaker, Gaetan Donblanc. Gaetan?
Thank you, Jay, for the introduction, and thank you all for attending this webinar from Cell Can to Battery Module. So today, Dr. Spotnitz and I will present to you a two-part study about battery modeling. We'll start with the characterization of a commercially available cell in Battery Design Studio, and then we move on to the study of the electrothermal performance of a full battery module in Star-CCM+. But before presenting to you this study, I'd like to introduce you to the modeling tools that we have used for this work, and in general to the battery modeling tools that we offer at CD Adapco. And so we have a set of different battery modeling tools that can address different length scales. They are represented here with these four rectangular boxes. And we start with our macrostructure electrochemistry level, whereby we can resolve the concentration and potential on the resolved three-dimensional macrostructure of an electrode. Then we have a tool to move on to the next scale, which is the cell level, where we have our cell design tool, namely Battery Design Studio, in which we can design the entire components of a battery cell from any shape. They can be pouch, they can be cylindrical or prismatic one cells. And then we can couple this to a performance model, and the performance model can either be physics-based or an equivalent circuit model. We can move on then to the module and pack analysis tool, which is namely Star-CCM Plus Battery Simulation Module, whereby we can study the flow, thermal, and electrochemistry performance of an entire 3D module or battery pack. And finally, our raw system design level, where we can couple our pack analysis tool, our cell design tool, to software such as Amazim or MATLAB Simulink to simulate the entire behavior of a full system, such as an electric car, for instance. But today we'll be focusing on a cell design tool. Dr. Spotnitz will present a study with Battery Design Studio, and I follow on a study on the pack design tool, Star-CCM Plus Battery Simulation Module. So just a few words about the study of today, just the highlights. We'll be characterizing a cell from a commercially available cell that you can see on the screen, and we'll be dissecting this cell and then characterizing it in a Battery Design Studio. The model in Battery Design Studio then will be validated, and then the cell performance will finally be improved. Then I will use this characterization to move into Battery Simulation Module to build up a 3D battery module and then study the electrothermal performance. Okay, so now this is my pleasure to hand over the presentation to Dr. Spotnitz for a study on Battery Design Studio.
Okay, so thank you for the introduction, and let me go right into the presentation. So we're going to start off with the design process for Battery Design Studio, and then we're going to talk about a specific high-power cell and how we experimentally characterized it in terms of both testing and the dissection. Then we're going to use a physics-based model to fit the cell properties. And with that physics-based model, we're going to go through a couple of case studies. We'll look at the effect of current collector thickness on the cell behavior and also the tab position. And then finally, we'll use the physics model to parameterize a empirical circuit model, the RCR model, and then hand that model off to Gaetan to use in the PAC simulation. So the cell design process for Battery Design Studio is this, and the first step is to specify the physical cell description. So that in that step, the dimensions of the electrodes, the separator, the packaging are all specified. And all that physical cell information is stored in what we call a text battery model, or TBM file. And this TBM file is a text file. You can copy it and distribute it to other people. After the physical cell description is entered, the next step is to enter the model parameters. And usually that's done by fitting to experimental data. And once those parameters are available, they're also stored in the same text battery model, this TBM file. And now this TBM file has all the information it needs to simulate battery performance, so it can be used or given to someone else. The key feature of Battery Design Studio is that the cell design and the model, the simulation model, are integrally coupled, so that if you make a change to the cell design, that's going to be reflected in the performance of the model immediately. And that's really the unique feature of Battery Design Studio. So moving on to the actual cell we're going to characterize today. This is a high power cell. It's a UR18650W, so it's 18 millimeters diameter, 65 millimeters tall. This is from the manufacturer's data sheet. It gives you the specifications. It's a 1.5 amp hour cell. We selected the cell because there is a lot of interest in it. It's been used in a couple of publications that are cited here. And so we're going to use this cell. The first thing we're going to do is take the data sheet and digitize the discharge curves from those data sheets. And so this is, again, from the manufacturer. The solid lines are the data sheet, and the points are the digitized values. We independently validated the values on the data, the discharge data. So this shows the lowest rate, the 1.5 amp discharge, and the highest rate, the 10 amp discharge. And the solid lines are from the data sheet, and the dashed lines are experimental values that we determined through independent testing. So it's a very close agreement with the manufacturer's literature. The next step is to dissect the cell. And so this is what the cell looked like, fully assembled. We took it out of the can, we unrolled it, and we measured the electrode properties, and the thicknesses of the electrodes, the thickness of the current collector, the tab positions. And then we took all that information and went to Battery Design Studio. And so the first step in Battery Design Studio is to specify that physical cell description. And we got a lot of information from the dissection. In this case, it's a cylindrical cell, so we picked a cylindrical cell in Battery Design Studio. And then we went to the individual components. So the positive electrode had a center tab, so we picked a center tab design, and we entered in the width and the position of the tab and all the other information, the coating thickness and the coating loading. The formulation we didn't know, so we had to make a guess, and we'll come back to that a little later. And then for the naked electrode, it was the tab design was a tab on one end. So we specified that design and entered in the parameters that we measured from the dissection. And again, for the formulation, we just made a reasonable guess in terms of what the composition was. But we did measure the thickness and loadings. Okay, for the actual formulation of the positive electrode, we knew from the publications that were cited earlier that the positive electrode was a mixture of nickel cobalt manganese, NCM, and lithium manganese oxide, LMO. So for the NCM, the voltage curves, we took a commercially available material from their website and got the voltage curve. And for the LMO, we also got the voltage curve from a website. For graphite, the voltage curve is well known, so we just took a graphite voltage curve. And then using these voltage curves, we adjusted the amount of LMO in the blend in order to get a good fit to the low voltage, the low current discharge curve. And that turned out to be the best fit we got was 80% NCM, 20% LMO. And that gave us a capacity very close to the manufacturer's specified value, and the voltage curve looked like a good fit. So here's the summary of the build report after entering in all the physical cell description properties. So we have a cell capacity, 1.5 amp hours, watt hours per kilogram, watt hours per liter are very close to the manufacturer's values. The cell weight comes out to be 42.9 versus what we measured experimentally, almost exactly the same. I should note this is a little bit different from what's on the manufacturer's data sheet. So the actual measured value agrees with what we calculated. So overall, we have some confidence that we have the right parameters because everything adds up to what we see experimentally. A Battery Design Studio allows us to generate a graphic of the jelly roll. And so here you can see the negative tab is on the outside of the jelly roll, and then the positive tab, it's about 40% of the way in, and you can see it here. This shows the simulation result compared to the experimental data. So this is the low rate, the 1.5 amp discharge, the C rate discharge. And you can see the agreement between the simulation and the data is very good. Now this shows the high rate simulation. And in order to fit the experimental data, we adjusted the resistance of the SEI on the negative electrode. And that allowed us to get a reasonably good fit for the 10 amp discharge. And that's shown here. Now, we fit the voltage curve, and we just looked at the resultant temperature prediction. And so this shows the actual experimental data from the testing versus the simulation. And you can see the final temperature is actually really close. There's a small discrepancy at intermediate times, about 2 degrees. And that could be because in the simulation, we represent the battery as a lumped model. So we take the average temperature of the whole battery, whereas experimentally, we're just measuring the can temperature. So there could be some gradient between the jelly roll and the can that accounts for that difference there. But overall, it's a very reasonable fit with this limited data set. Now, since we used a physics-based model to fit this experimental data, we can get some insight into the mechanisms for the voltage loss. So in this chart right here is showing all the different sources of voltage loss in the cell as a function of the discharge time. And this is the high rate discharge, the 10 amp discharge. So the largest source of voltage loss is this negative activation overpotential. And so that comes from that SEI resistance on the negative, which we adjusted. So that's an assumption that that's where that voltage loss is coming from. The second largest source of voltage loss is the ohmic drop. And so that's in the current collectors and the tabs. So it is significant for these high rate discharges. Then the third and fourth have to do with the electrolyte properties. There's the diffusion polarization, so that's the voltage loss that develops because of concentration gradients in the electrolyte. and the ohmic loss, so just the IR loss and the electrolyte. So those two terms together would actually sum to be the largest source of voltage loss. And so the electrolyte plays a critical role in these high power discharge. And then the other terms are pretty small. So in terms of our cell design, what we're going to look at is the effect of the ohmic drops, the current collector. And so we're going to explore this, how we can change this source of voltage loss. The simulations show us what's happening inside the cell in terms of the distribution of potential across the electrodes. So this top chart is showing the positive electrode, and the tab is about 40% of the way in, and you can see that there's a more significant voltage loss from the tab to the far end, whereas the tab to the other end, the potential is more uniform. On the negative electrode, the tab is on the end, and so you can see a steady voltage loss across from the tab down to the end. The scale here is 0.3 to 0.34, so about 40 millivolt maximum for the positive, and on the negative, about 100 millivolt drop. We can also look at the current density distribution, so that's the amps per meter squared flowing out. And again, if we look at the positive electrode near the tab, we see that there's a higher current density on the right side here, and then the current density on the left side as you move away from the tab decreases and pretty significantly. If we look at the negative electrode, the tab's on the end. The highest current density is right there by the tab, and then as you move away from the tab, the current density decreases steadily. And just from the scale here, you can see it's about 160 amps per meter squared max down to about 100, the minimum value. So about a 50–60% variation in current density across the electrode. Okay, so now that we have this model, we can start exploring design changes to it. So let me go through this slide. First of all, there's in this pink here is the base case design. So this is the actual design of the manufacturer, with the positive having a center tab and the negative tab at one end. And so 7A is our base case and in this base case, we're showing the thickness of the collectors, the resistance of those collectors in milliohms per centimeter, and then the ratio of the negative to positive. So we can see that the positive resistance and the negative resistance are close to 0.9. So positive resistance is a little bit higher. And that generates about 0.88 watts of heat, and it gives us an energy density of 133 watt-hours per kilogram. So one thing that, if you notice, that the current on the negative has to go the entire length of the electrode, whereas the current on the positive only has to go half the length. So one idea would be to make the positive resistance twice as large as the negative. And so if we do that, so we increase the thickness of the negative collector, that's going to decrease its resistance. And so now we get a ratio closer to 0.6. And if we do that, sure enough, we reduce the heat fairly significantly, about 25% reduction in our ohmic heat generation. But the penalty we pay is by making that negative collector thicker, we have that heavy copper collector, and so that gives us a hit in the energy density of the cell. Now, for the same energy, it weighs more. So another approach might be to make the resistances the same and make them higher. Increase the thicknesses of both collectors. So now we're going to reduce the overall resistance of the cell. And if we do that, now we're balancing them, so the resistance of the negative and positive are about the same, but lower values in the base case. And we see that it doesn't really have much of an impact on our ohmic heating at all by doing that, and a small impact on our energy density. So another thing would be to increase the thicknesses of the current collectors, so we reduce their resistance but this time keep our same ratio of 0.6. And if we do that, now we see a very significant impact in the ohmic heat generation, and unfortunately also a big impact on our energy density. So to optimize this cell design using the same tab configuration, probably our best bet would be to to increase the negative collector thickness a little bit, and that would reduce our ohmic heating significantly and with a small loss in energy density. Now, another thing we can explore is a different tab design. And so this case 8 tab design here, now we're adding a second tab on the negative electrode. So this would cause some challenges in the manufacture, but we can at least evaluate what the benefits would be to see if this is a useful direction to go. So as our first step, we're going to use our same current collector thicknesses, or very close to the same, and we see that by doing that, we cut our ohmic losses in half immediately by using the second tab on the negative electrode. And our energy density actually increases slightly. So we half the loss, the ohmic losses, and we increase our energy density by adding the second tab. Now, another thing we could try is reducing the current collector thickness, because and keep this similar type of ohmic heating loss. So if we cut our collector thicknesses in half, so this is the 8AK, so now we have very thin current collectors, we can see that the result is that the ohmic heating is still less than our base case, but now we've increased the energy density of the battery to 150, so a very significant increase over the base case design. So if we could develop a manufacturing process to use 2 tabs on the negative electrode, we could really see a significant improvement in performance for these type of high power cells, even the small cell. Okay, so I want to move on to now creating an empirical model just to represent the voltage behavior of the cell, so that we can do electrothermal simulations of packs. And for that, it's beneficial to use a simple circuit model. And so what we're going to do is use our physics-based model to run HPPC tests. These are hybrid pulse power characterization tests. And this graphic right here shows what the test looks like. So basically, we're doing discharge and regen pulses at 10% state of charge increments to characterize the resistance of the battery as a function of state of charge. And we could do that for several different temperatures to see how the resistance varies as a function of state of charge and temperature. The advantage of using this HPPC test is that we can use this gap tool in BDS, shown right here in the second graphic, to automatically generate the model parameters. And so that's this table right here. And so we have the time constant, the open circuit voltage, and the series and parallel resistances. When we do the gap analysis, we get the units in terms of ohms. So we have to convert them to ohm meter squared to make them more general for use in a model. And so that's our final step. We convert these resistances to ohm meter squared, and now we can copy it into the RCR table model in BDS. And we're ready to simulate the 3-dimensional behavior of the battery in a very computationally efficient manner. And just to validate how good the fit is, this slide shows the HPPC results for the physics model versus the circuit model. And then if we blow up a couple of the pulses here, we can see that the fit is very good, really just off by a very slight amount for these 2 cases. Okay, so we've designed a cell, or generated a model based on a commercially available cell design. We used the inputs to that model, the experimental data and dissection of the cell. If our materials developer had used Battery Design Studio, they could have provided all those properties that we needed for the model using a TBM file. but in our case, we did it independently. And then once we have our TBM file, we can hand that off to a pack or module developer, and they can use it in Star-CCM Plus to design a pack, a battery pack. And that's what we're going to do. So I'll hand it off to Gaetan, and thank you very much for your attention.
I would like to thank Bob for his presentation, and let me start now with the second part of this study, which is the analysis of the thermal performance of a battery module. This is the agenda for the second part of the study. I will briefly go through an introduction, then we move on to the build-up process of the module. I will present to you some analysis and results, and finally we move to improving the design of the current model that we've run, and I will conclude with some lessons learned and next steps. Well, the objective of the study is to simulate a battery module thermal performance. We will be using a high power cell previously characterized in Battery Design Studio and previously enhanced by Bob Spotnitz, and I will use it to build up a full module, and adding all the components of the cell, the can, jelly rolls, tabs, etc., but also the components of the module, the casing, the electrical installation pad, the bus bars, cooling system, etc. I will also apply to this battery module a drive cycle, namely a US06 drive cycle. So below you can see a table of the different specifications of this battery module. So it uses this 18650 high power cell. The module assembly is 12S4P. It's about 45 volt nominal voltage, and the energy is about 275 watt-hour. How do we build such a model? What is the process? Well, it all starts with Battery Design Studio. We've seen with Bob Spotnitz that we've taken a commercially available cell and we've characterized this cell. We need to obtain its geometrical specifications as well as characterizing its performance. All this information can be saved and stored into one file, the text battery model file, TBM file. This TBM file will be then transferred to battery simulation module. With the information contained in the TBM file, I can obtain straight away a 3D representation of that cell in Star-CCM plus BSM, and then I will use this cell to duplicate it in the configuration of the module I want. Also contained in the TBM file, there is the performance model specifications, and we're using an equivalent circuit model here in this case. So coupling the geometry, the cell performance model, the thermal solver of Star-CCM Plus and the fluid solver of Star-CCM Plus, I can run a full simulation to study the overall evolution of the temperature of a battery pack under a complex drive cycle. Importing the cell into Star-CCM Plus battery simulation module is a rather straightforward process. All I need to do is selecting this file and adding it to my simulation. So doing so by adding the file, deciding whether I want to build all the components of that cell, and I want to do this, can, tabs, etc. And in a matter of seconds, I can obtain a 3D representation of that battery cell. Having imported the cell information with the battery performance model, I can now build the battery module. I need 12 cells in series with 4 rows in parallel. Using the dedicated preprocessor, I can specify some spacing between the cells, defining some orientation of the cell as well. Very quickly, the preprocessor will help me duplicate the cell and then generate the battery module in the configuration I want. Adding the other module components, such as the bus bars, the electrical installation pad, the cooling channels, the casing, can be done with Star-CCM Plus 3D CAD tool or any third-party CAD software. So we've now built a full geometry of the battery module. We have the configuration of the cells, and we have the cooling channels, the casing, etc. We now need to discretize this domain. And so to do so, we will use the Star-CCM Plus automatic meshing capability, and especially using the thin mesher, which will be used to optimize the control volumes count in the thin geometries of the battery cells. In total, we have about 5.5 million elements for this simulation. After the meshing is done, we have to specify certain properties on the different parts of our model. I'm listing here the most noticeable properties for these parts. For instance, the J roll with the anisotropic thermal conductivity. We can notice that the radial direction for that thermal conductivity is quite small compared to the other directions, theta and z. Also reminding that we are using for the cell performance model, the equivalent circuit model that we name RCR, and that was prepared previously by Bob. Also in the coolant, we are using the liquid ethylene glycol at 10 degrees, and here are the thermal properties. The electrical insulation pad is a multipurpose silicon sponge rubber with this quite low thermal conductivity. The cells can and housing are made of steel. The negative current collector will be made of copper, and then all the other parts will be assigned with the aluminium physics properties. Now that we have almost completed the setup of our simulation, we need to specify certain conditions, especially what are we going to apply to the battery module. Well, we say we wanted to apply a drive cycle, and here it would be a USO6 drive cycle. You can see on the left hand side the evolution of this drive cycle in terms of vehicle speed that we've converted into current versus time on the right hand side. This will be applied to the battery module. The initial temperature for the battery module will be 25 degrees C. The coolant which flows into the cooling channels will be set at a constant flow rate at a temperature of 10 degrees C. And then finally, we can run the simulation on a workstation, desktop workstation, multiprocessor, or on a supercomputer. Let me show you some results out of this simulation. I'm showing here the battery module. You recognize it, with the battery cells sitting in the casing and connected to the bus bars. I'm plotting here the temperature distribution on the domain. In our case, this is rather important to look at the temperature distribution. Creating our design, we want to ensure that it will present the most homogeneous temperature distribution to ensure the best electrical performance, but also the longest life expectancy for the battery cells. Looking at the jelly rolls themselves, I can notice the rather large temperature difference across all of them. Even looking at the inside of the jelly rolls, we can notice this temperature spread for each of them. So we need to have a bit more investigation on why we have this large temperature difference inside the module. So plotting the temperature difference evolution inside the jelly rolls, I can notice that it can be as high as 10.5 degrees towards the end of the simulation. So if I look at the reason why it seems that we have this really high temperature difference, looking at the cooling channels, it seems that the back of the channels are barely receiving any cooling. And this is the reason why I'm heading up with those really high temperature cells toward the back of the module, when the front of the module is receiving some good cooling, and so therefore the cells are much cooler in this case. And so looking at the average temperature evolutions for each jelly roll, I can notice this really wide spread of temperatures inside the entire battery pack. Especially at the top, I can see those really high cells, which are the cells towards the back, high temperature cells, which are the cells toward the back. And then, some other cells here at the bottom who are receiving a good cooling. And so this shows the really wide spread of temperature inside the module, and eventually can affect the overall performance, the overall electrical performance of the battery pack. And indeed, if I look at the electrical performance of the cells, I can notice that this temperature difference is affecting the voltage evolution. So if I look at this voltage evolution, which is all the different J rows plotted here on this graph, and if I look at the area where the temperature difference was the highest, so towards the end of the simulation time, by looking at the spread of voltage distribution across the different J rows, can notice that the difference inside the module is about 40 millivolts, which is also quite noticeable. This will affect obviously then the heat generation in the cell, since it's depending on the voltage evolution, and then still looking at the same area where the temperature difference is the highest, so towards the end of the simulation, I can notice that the spread of the heat generation inside the module is about 0.3 watts. So this kind of spread helps understanding where this spread is affecting the performance on the battery module. We can notice that the hottest cell, they are the ones who show the highest voltage and then the lowest heat generation, and then the cooler cell are the ones showing the lowest voltage and the highest heat generation, as we would expect. Obviously this kind of performance is rather poor. We need to find a way to reduce that temperature difference in order to better improve the electrical performance of the battery module. So is there a way we can improve the design, the configuration, the conditions of the battery module in order to get a more homogeneous temperature difference to improve this electrical performance of that battery module? So this is what we're going to see next. What I would like to achieve here, what I want is improve the design to reduce the temperature difference in the jelly rolls. And so I would have to make changes on my geometries or on my conditions in order to reach that objective. So to do so, I will use Star-CCM plus Optimate Plus add-on. This is installed as part of standard Star-CCM Plus installation, and it has an environment to set up design exploration campaigns. This is what I'm going to do. I can set up the baseline model in Star-CCM Plus, and then Optimate will perform the following for me. It will create all design variants and input files. It will submit and monitors running jobs. It will collect the campaign data and post-process the study. So in my design exploration study, I will focus on the design of the cooling channels. I will parameterize the geometry of the cooling channels to modify the channel's diameter. As you can see on the left-hand side of the slide, I will also parameterize it to modify the number of transversal channels, as you can see on the right-hand side movie. And finally, I will also make the variation of the coolant flow rate. So for all of these inputs, I will give a range of values that the Optimate would use in order to make changes into the designs and conditions for the coolant flow rate. Then the objectives I've set for my study are two. I will specify a constraint. So what I would like to do is to ensure that the design I'm setting helps me to reach a temperature difference in the jelly roll that is less or equals to 2 degrees. But also, this design should minimize the pressure drops in the channels. So let's have a look at some of the results out of this design exploration study. At the top, we can notice the temperature difference evolution for the original case, the base case. And at the bottom, I can notice the temperature difference evolution for all of my improved designs, and they are really showing a much better improvement in terms of the level of the temperature difference inside the module. If I isolate the base case and the best design, the best case that we've obtained, it shows towards the end of the simulation an improvement of about 7 degrees, which is quite substantial. However, we haven't been able to reach the temperature constraint that we set, which was to be below 2 degrees temperature difference inside the module. So we still have some room in order to improve this design by probably changing the cells configuration or again modifying the conditions on the cooling flow rate. And finally, if I look at the temperature distribution based on the findings of the plot that we've just seen, looking at the first original case with this really high temperature difference across the module. Now looking at the same temperature distribution but on the improved design for the cooling channels, I can then obtain a much more homogeneous temperature distribution inside the module, which will help obviously with the electrical performance of the module, but also with the life expectancy of these battery cells. So as a conclusion out of this study, the first study of the battery module electrothermal performance revealed a significant limitation of the cooling plate to ensure homogeneous temperature and distribution. And this temperature imbalance strongly affects the module electrical performance. And so in the objective of improving these limitations and these poor performances, the design exploration study that we carried out helped improving the best case design by improving the temperature difference to up to 7 degrees in some cases. But also it revealed that even though we tried improving the cooling systems, we couldn't manage to obtain the target temperature difference that we set, that is to reach a 2 degrees temperature difference across the module. And so to conclude, there is still room to improve these designs, and then the next step would be then to meet the 2 degrees temperature difference criteria, but also going further by not only looking at performance in normal conditions, looking at what happens in hazardous conditions, such as the heat propagation in a thermal runaway scenario. Finally, let me just add a few words of what is coming up next. Tomorrow, the 10.02 Star-CCM Plus and Battery Design Studio will be released. On the battery modeling side, the new features will be an enhanced post-processing, as well as an enhancement on the equivalent circuit models. We'll be able to handle 2RC as well as NRC models. If you want to talk to us, we will be at the Detroit 2015 AABC. We will be presenting and hopefully presenting some improved results on the current design. And finally, if you want to find out more about our battery tools and our overall solutions, you can go on to our website. Thank you very much for your attention.
Just remains for me to say thank you to Bob Spotnitz. We really appreciate you recording your material for us, and of course thank you to Gaetan for his contribution too. With that, we are out of time. Thank you all. Goodbye.